Today I'm going to talk about GPU parallelization of two-way coupled particle fluid solver. So I'm Prasad Perlekar. I am a faculty at TIFR Hyderabad. And the work I'm going to present today is work done with a strong collaboration with my graduate students, Navdeep and Vikash. So Navdeep is in Max Planck Göttingen and Vikash is in Sweden, in Nordita. And also whatever we have done is with generous amount of help from various colleagues in NVIDIA, and I list them here: Doris, Gaurav, Prathu, Mahesh, and Hemant. And I'll surely point out as we go along what are the contributions of these different people in what we are going to discuss today, namely the GPU parallelization of two-way coupled particle fluid solver. So the reason we are interested in such systems is because particles in flows are present in a variety of situations. In atmosphere, you can think of aerosols in clouds or volcanic ash, and also bubbles in oceans. And indeed, because there are these variety of applications, we like to understand the physics of these systems by doing numerical simulations. And here are some realizations of the numerical simulations that we have been interested in. These constitutes of bubbles in flows or flows generated by suspension of bubbles, or particles in rotating turbulence which have geophysical application, namely the physics of cyclones and raindrops trapped inside them, or a simple problem of how does a bunch of sand particles, which are all organized in, let's say, a droplet-like position, how do they sediment and what happens to the various instabilities that they undergo as they are sedimenting. And as you would see that very quickly a cloud of droplets decomposes becomes a torus kind of a structure, and then it further disintegrates into a complex spatio-temporal structure. And one would like to understand what is the physics behind all these systems. What are the key challenges here? The key challenges are that in all the problems that we have looked at so far, and which are summarized over here, there are multiple length and time scales that are excited. The numerical simulations typically require very large system sizes, which straight away boils down to having large memory on your system. And also you want to integrate the system for physically relevant time scale. So you want a very long time integration. And so, as also the previous speaker pointed out, that we want speed, we want very fast simulations. And the kind of problems we are looking at, in these problems, particles modify the flow and also interact with each other via the fluid medium in between them. And so that's typically called as the hydrodynamic interaction. And that's the physics that we would like to understand. The way we do this physics is via the flow is solved using Navier-Stokes equation, which is written over here and which also the previous speaker pointed out. And this equation is coupled with particles. So you can think of now a bunch of water droplets which are falling. So here U denotes the velocity of the fluid. Rho0 is the density of the fluid. Capital F here is the force acting on the fluid. And similarly, because you have particles inside, the equation for particle is that the rate of change of position of particle is equal to the velocity of particle. And in the simplest scenario that I would talk about today, you can think of the velocity of the particle is given by the velocity of the fluid at the particle position plus a force term at the particle position. So you can think of the system as a bunch of particles or bunch of rocks which are falling down. And the reason they are falling down is because there is gravity, and this force could be the gravitational force on each of the particles. So what is the strategy? How does one go about simulating such a system? So the fluid typically lives on a grid. So here is a schematic. So the fluid velocity field is defined on grid locations, and the particles are present on the off-grid positions. So you can think of a cloud of particles as shown here. Now, as I pointed out, that the particles, each of them is feeling the force of gravity. And then because of Newton's second law of motion, whatever force is acting on the particle, equal and opposite force is put back onto the fluid. So the way one simulates is the following, that you first evaluate the force on the particle. Then from the particle, you interpolate the force into the grid locations of the fluid. Once that is done, now we know what is the force because of the particles at the grid locations. So you update now the velocity field in the Navier-Stokes equation with the force that one has. Now that the grid locations here have been updated with the velocity, the next thing you do is you then interpolate the velocity at the particle positions. Once that interpolation is done, then you, and this is done for, of course, each and every particle. So once that is done, you move the cloud to the new location by solving the second equation over here. So these steps that I pointed out have been written down over here in an orderly manner. The shaded region over here somehow is an indication of what is a typical range over which you would use particle information for interpolation as well as extrapolation. And this range, although here shown as roughly a single grid location, typically what we do is we choose this thing to be slightly larger, and its influence is over 2 lattice spacing each side of the particles. And we do simulations, of course, in 3 dimensions because that's where the real physics is. So this is the system that we want to study. And clearly, again, for the Navier-Stokes, even the previous speaker pointed out that it's a big challenge to simulate these equations fast. So the way we do it is the following. So that would be the part 1 of my talk, where I would discuss how one solves the Navier-Stokes equation. And this is part of an ongoing collaboration with NVIDIA, again done with 2 of my graduate students, Navdeep and Vikash, where what we have done is we have managed to port our code onto a multi-GPU framework using both cuFFT library for Fourier transforms or the more recent cuFFTMp library. The details of how the porting was done on the multi-GPU framework and other things, I'll give a brief overview today, but details you can find in this blog and a previous GTC talk whose link is provided over here. Once I tell you how do we integrate Navier-Stokes equation and the kind of speedups that one observes, we will go over to how does one implement particle-fluid interaction. And that work, the MPI implementation was done by Vikash and Navdeep, and the OpenACC porting is done by me and Prathu and Hemant Giri from NVIDIA. So let's go ahead and ask, how do we solve the Navier-Stokes equation? Being a physicist, we would like to solve them as accurately as possible and in simplest possible boundary conditions. So what we choose are periodic boundaries. And if you choose periodic boundaries, then you can use what are called as Fourier transforms, of course. The advantage of that is that the dispersion relations in Fourier space are also exact. And so if you take Fourier transform of this equation, you get the following equation where ui hat are now the Fourier coefficients, which are obtained by Fourier transforming the velocity field u. And this equation, the one on the top, simplifies to actually this equation where u cross omega, omega is the vorticity, which is curl of velocity field. So you have to evaluate this term and then take a Fourier transform of it. And it turns out that this is the most expensive operation in the system, because if you ignore this term, the system otherwise is a linear system, which you can solve analytically. So then the whole thing is, how can we solve this very fast? And this was pointed out by Orszag, that one could do it using what is called as a pseudo-spectral method. So what we do is we start with the velocity in Fourier space, real space, we Fourier transform it, get the Fourier coefficients. From the velocity Fourier coefficients, we obtain the vorticity Fourier coefficients, inverse Fourier transform the both. So now we have velocity and vorticity in real space, do a product of the two, rather cross product of the two, whatever you get, you do a Fourier transform of it back again. And then you get this u cross omega term in Fourier space. Now remember, because we are working in 3 dimensions, the velocity field has 3 components. So when I write Fourier transform of u, indirectly what I mean is that one is doing 3 fast Fourier transform to get the velocity coefficient in Fourier space. So overall, to do the pseudo-spectral convolution, one is required to do 9 Fourier transform. So that's the most time-consuming step. And the time marching then we do using a second-order exponential Adams-Bashforth scheme. What are the bottlenecks in the standard turbulence thing? Because we want to do physically large Reynolds number. As you increase the Reynolds number to have well-resolved structures, your grid number of grid points that you need to do increases drastically. Actually, they could increase like Reynolds to the power, roughly like Reynolds square, which is a very large number. The bottlenecks are indeed, as you want to do larger and larger Reynolds, you are required to do bigger system sizes. And you can straight away appreciate that even for a 1024 cube simulation, you would be required to use 72 GB of RAM. FFTs are an expensive operation on any multi-node framework because one is required typically to do all-to-all transpose to perform the Fourier transforms. So how do we, and these are the typical time scales, and to emphasize to you that over past 40 or 50 years, people have been pushing very hard, starting from the initial works of Stephen Orszag to do a very small 32 cube DNS using the pseudospectral method, to the more recent works at 16,000 cube DNS, which were done on Earth simulator in Japan, or with really 16,000 or 32,000 cores on Blue Gene kind of architectures. But however, most production runs that one typically does varies between 1024 cube to 8.92 cube DNS. And so what we do, or what we have done over many years, is we have solved these equations, of course, on the standard MPI implementations with Fortran 90. Not only that, but we have also managed to port it over multi-GPU frameworks using either the native cuXFFT, where you use multiple GPUs within a single node of a DGX box, or the more recent cuFFTMp library developed by Doris Pan and colleagues at NVIDIA. And we have implemented both OpenACC and CUDA in Fortran implementations. And I'll just point out to you how easy are certain code parts to use within the OpenACC framework, and our code is maintained over GitLab. So this is again an overview of what I pointed out. And so let me just go ahead with that. What is the framework within which we work? We use real to complex and complex to real transforms, which are D2Z, Z2D transforms. We do slab decomposition, which employs NX, NY, NZ collocation points. In real space, the data is decomposed primarily in the slowest direction. Remember, we are doing Fortran. So the data decomposition happens in the third direction, which is Z. In the Fourier space, the data decomposition happens in the, it's permuted. So the data gets divided along the y-axis. And the philosophy we work with is 1 GPU per MPI rank. So we don't have, at least for now, parallelization where you have 1 GPU and multiple MPI ranks going together. We work with 1 GPU per MPI rank. So I won't go into the CUDA Fortran part, but the OpenACC part looks very easy. All the do loops are collapsed and with just pragma added for the OpenACC part. And that's how we parallelize it over OpenACC. And what I would show you quickly are the results that we obtain. So the first thing is that we do see that a Navier-Stokes solver scales very well over multiple GPUs. I haven't shown in here explicitly, but we observe a strong scaling with number of processors, which at least for 1024 cube goes as good as P raised to 0.8 or close to that. And then, we of course did benchmarks for the exact solution of Navier-Stokes and also obtained very nice vorticity fields of turbulent flows. And indeed, whatever we observed was indeed consistent with the FFT timings, because as I pointed out, 70% of the time goes in doing fast Fourier transforms. And indeed, what we observe is that as we go on increasing the number of GPUs, our performance can, so for 16 GPUs or 8 GPUs on DGX A100 for fast Fourier transform of 2048 cube, the performance could be as good as what one observes for the same system size with as high as 2 raised to 16 cores of Blue Gene P cluster. And okay, this is the scaling which I pointed out. And of course, double precision is typically, or single precision is twice as fast as double precision. So I'll go now quickly over to the next part, which would be just 2 slides on how to do the particle parts. So as I said earlier, there are 2 routines which are very crucial over here. One is the interpolation of velocity on the particle nodes and extrapolation of the velocity on the grid of the forces on the grid nodes. So what we do is for velocity interpolation, we go over all the particles and we use the reduction operation to obtain the velocity at each particle position, because all the grid locations have to send information to the particular particle point. And for that, indeed, one needs to do reduction operation. As I pointed out, interpolation is done using 2 delta x grid locations in the vicinity of the particle. For the force routine, on the other hand, because you have all the particles are now writing the data onto the neighboring grid points, what we have figured out was that the reduction operation is no longer possible now, because then each thread would be required to have the big force arrays, which is clearly not possible. Rather, what is the right way to go ahead is the atomic update. And using that, we found the performance to be very good. The rest of the loop, of course, as you see already, between the 2 cases is very identical. What are the speedups? So we started with, as a benchmark thing, just with 10 particles on a 64 cube domain. And you see that most of the time here was done in evaluating fast Fourier transform. And because FFTs are already well optimized, the 34x speedup was observed. We did some more optimization, and in the final stage of the code that we had now, for 10 particle, at least we were able to squeeze out 6x speedup. And for FFT, we got a 65x speedup. But now as we go on increasing the number of particles, so with very large number of particles, you clearly see that the time on the CPU for the particle update is now an order of magnitude larger than the FFT things. And here, when we redid our calculations, we found that the GPUs indeed were squeezing out their full performance. And indeed, you get close to 80x speedup, even with particles present. So that's very good. So now we have a code where we have both the fluid part as well as the particle part fairly well optimized. So I'll stop here with these recent movies which I made on August 18 for a benchmark of what happens for a sedimenting particle. What I would show is that GPU framework is indeed a good alternative, and indeed we saw very good performances on DGX architecture, both with CUDA Fortran and OpenACC parallelization. And right now we have started to work on writing multi-GPU modules even for the particles to get even better performance. Thank you.